So think about this question. Explain the meaning of function is continuous at a point P. So where do we start? What do you guys thought about this? Yeah, so you have to define what function is. What kind of function are you talking about? Right? Yeah, so what is the function? And also what do you guys have thought about? Path?
It doesn't really matter what path you choose, so it eventually gets into one point. It's continuous.
Okay, so you want to explain by path? So continuity by path, or somehow you want to talk about independent paths. Okay, so what else?
And then is the function continuous at exact point at the
Exact point and what?
at point P.
At point P. Yes.
At point P. Can we use like limit?
Yeah, so we can talk about the limit. Okay. Anything else?
That's all.
That's all?
Yes.
Anyone else? Okay, if you want to just, so so if you want, everyone wants a good grade, right?
Yes.
So you want to try out whether your thinking is correct or not. Or are you going to just test out that in the midterm? Just test it out right now. Just share your ideas. So you have something is written in the paper, so it's easy to say it. Yes. Who's it? Yes.
Epsilon delta?
Yeah, okay, so we want to talk about epsilon delta. Okay. Anyone else? So you have, if you thought about all the ingredients, it's now time to think about how to organize it. So basically, when I ask this question, I don't want a one sentence answer. I want the essay, basically. I want the line of thought, right? So if you want to start with a function, okay, so what is a function? What do you, so you have to make a frame of thoughts. So in what context are you going to explain the continuity? So everyone has some kind of example in their mind. If you're thinking about the single variable function, you have to specify what is the function you're thinking of. So let's say you can start from, let's say your function is single variable function. Then you'd have to define what single variable function is, but at least you have to mention it. And then what is the meaning of the point in this case? So we're talking about the point in the domain, right? So you have to clarify every word in the sentence, and then at least you have to specify the meaning of each word, and then you can now talk about the continuity. You can talk about the continuity of single variable function at a certain point or a value as a limit, and also you can talk about it as an absolute delta. And also you can talk about it as a path. Maybe you can go from the left or right to the same point, whether your limit is the same. So basically it has the limit. But everything has to be explained. So of course, so you might ask, okay, so what's the basis of grading then? Okay, so maybe this is the vague questions I can ask for the quiz, but in the exam, I will be a little bit elaborate in my questions. So if you want to try to explain the continuity with the limit, I want you to explain more about what's the meaning of this symbol, right? So if x goes to p, fx, it goes to some number, what does that mean? What do you mean by whatever written in here? You want to explain more about this. And also, it's not single variable function we always talk about. We always talk about multivariable function. So what do you mean by multivariable function is continuous? Let me define it this way. So you can classify function, well, it's not entirely comprise all the functions, but into three types at least in our case. So this is single variable, this is multivariable, these two are multivariable. What's the difference between the second and third? So we usually write the first one as y equals to f of x, and second as z equals to f of xy, or when it's three variable function, it's x, y, z. So it determines a single number with two or more variables. These two or more variables are called independent variables. What is the difference in the third case?
Two or more variables as a result of.
Right, so you have more than one variable dependent on the independent variables. So we usually write it as x1 to xn. So these are independent variables, and it determines m. So you see that m dimensional. So you have m coordinates of variables that is determined by these n independent variables. So basically, if you see carefully, each yj are dependent on n variables. So you can say this is exactly same as splitting this function into set of equations. Y1 equals to some formula in terms of x1 to xn up to ym fm x1 to xm. Here f1 and fm is just meaning that it's a formula. There is a formula determining yj. So you see, by looking at this case, it's same as this case, right? So you want to explain the continuity all in three different cases. So maybe this is obvious, at least, and intuitively clear. And this might be a little bit intuitive, because you can say by path, or like path independent, or some kind of a limit. But how about this? How do you explain the continuity of this kind of function? So you want to have a point P lies on the domain, and you want to say the function is continuous at that point. What does that mean? What does that mean? So try to explain with these ingredients. Which one you want to use? Do you want to use the limit? No? No? Our path? Path? Last one? Epsilon delta? Okay, so how do you explain by epsilon delta? So why do you need epsilon delta here? So basically, epsilon delta is just a statement to explain the symbol of the limits. So you need to have a complete statement, also intuitive idea what the statement is talking about. So I think we can we can talk about the epsilon delta after we talk about the limit. So let's try we can try everything here. So let's try the limit. So what does that mean that this function, this type of function, is continuous at P? So let's write naive notation. So I have x. So I'm going to write a symbol, a large X, for the n-dimensional point whose coordinates are xi. So if x goes to P, then I know that the fx goes to fp. So I take as if x and p's are the numbers in the single variable case. What does that mean? So here I'm taking the limit of what? A point, right? Fx is a point. When x is given in the domain space, the result is m-dimensional point. So these are points. Sorry. These are points. So what do you mean? You have to explain what do you mean by the limit of a point is a point. What do you think about this statement? Limit of a point fx is equal to f of p, which is another point. How do you say a point, the limit of a point is another point? What do you mean by that? What do you think it means by that? So imagine a point, just imagine a point, the point limiting to another point. What does that mean?
Goes towards.
Yeah, it goes towards that point, right? So how do you know that it goes towards that point?
You need to find the difference between.
Yes, so good work. So we need to find the difference between 2 points. What do you mean by difference between 2 points? It makes sense to say difference between 2 numbers, right? But how do you take the difference between 2 points? What do you mean by that? Distance, yes. Yeah, so distance. So, so difference can be many things. Maybe it can be vector, because vector also gives you the difference between one point to another. But we're not looking at the vector. We're not looking at specific direction. We're only looking at the distance between 2 points. When we say one point is approaching to another point, we say the distance between that points are decreasing to 0. So that's why we want to use the epsilon delta. So let me write the definition of this symbol. Again, this is not equation. This is a statement. Okay? So this means that for every epsilon, there exists delta such that for all x satisfying distance between x and p less than delta, the inequality holds. F of x minus is less than epsilon. Okay, that's what it means. Well, why do we need this complicated definition, complicated statement? Why can't we just say it goes too close to this point? Well, how do you prove that? So the question is, if you want to claim that is true, how do you prove that one point is closing to another point? You can try some few steps, you can try some path, but that doesn't explain, that doesn't prove that it always approaches to that point. It kind of gives you the evidence. So what do I need? I need the guarantee that if I want to get close enough, I have a certain range of my x around P so that every point around that P is going to lie inside of a small range of Fp. So here's the situation that I'm going to use a lot as a drawing. So when you deal with the multivariable function, you cannot draw the graph. So you have to separate out the domain and codomain space in 2 spaces. So let's say this is your domain and this is your codomain. You map a point in the domain space to another codomain space. So we have x here and you have f of x here. And this is your point P, which is fixed. And also this is the point P, Fp, which is also fixed. What I want is, if I make x to approach to P, I want fx to also approach to Fp. The only way I can prove this, which means that it always happens no matter what path I take, is I need to take a small neighborhood of Fp, like small neighborhood. I made it big, but it's small. And then I need a guarantee that if I choose my x pretty close to P, then every point around P will lie within the range of Fp in a certain distance. So this distance, the radius, this is epsilon, and this radius is delta. So depending on what epsilon, how small I choose for epsilon, I need a small enough delta so that this happens. So if I have this guarantee, if I have this map, if I have this rule of choosing delta according to epsilon, then I know that it always has to go to Fp. That's the meaning of the limit. That's what is going on. So you need to understand this in the mathematical point of view. Otherwise, this is the basic notion of everything that we're going to deal with in the multivariable calculus. Okay, so if you don't like this idea, there's another way of looking at this. So think about the equation I wrote when I introduced the classification. So another way of looking at the continuity of a multivariable function is that the coefficient or coordinates of each coordinates of m-dimensional point is going to approach to that coordinate of the target point. So I can rewrite this limit as the following. For each j from 1 to m, the limit when x goes to p of fj x equals to fj p. So now it's a bit different. You might say, what's the difference? The only difference is that we're not looking at the real number. We're now looking at the real number. The limit of real number is now real number. That's what it says. And we want that happen for every coordinates, j from 1 to m. Every j's coordinate. So you can draw the graph. No, maybe you cannot draw the entire graph of a function, but you can draw the graph of each coordinate function, which is fj. So what it says is that if you look at each fj coordinate function and you can see the continuity at the same point, then you can say the entire function is continuous. That's also exactly the same argument as we have here. The only difference is that we change the difference between the numbers into difference between the points into difference between the numbers. So you can replace the difference between the number points as just absolute value of the difference of numbers. So I'm saying that there is more than one answer. All right. Any remark on this? So the more you think about this, more you can get the better idea about this. And today we want to talk about the derivative of single variable case. So just for now, although we're not going to, the main single variable function is not the main topic of our class, but we need to understand the calculus on single variable function well in order to understand the calculus on multivariable functions. So we need to start from the derivative. So let's start from the definition of derivative. So what do you mean by derivative? So I think everyone knows it, I hope, but I'll rewrite it again. So a function, so here, for this class only, I'm going to assume our function from now on is single variable function, okay? So even though I started with the multivariable function, from now on, let's assume that every function I mention is single variable function. So a function f of x is continuous, differentiable at x equals to c if the limit exists. What limit? This limit. So everyone knows that. I think at least you remember what you learned that, okay? At least in the last semester or in high school. So I want to test you out with the possible meaning of this differentiability. So maybe I'm not going to write it everything, but let me mention by words that when the function is differentiable, this limit is called the differential, and it's denoted as f prime c or df dx, whatever. And also be careful that the differentiability is about a function and a point. So you also need two pieces of information, function and a point. Just the function doesn't give you anything about the differentiability. It doesn't make sense. But when you say a function is differentiable without mentioning any point, that means it is differentiable at every point in the domain by convention. All right, so the remark, or let's say think about the meaning of differentiability. Differentiability, okay, whatever. All right. So first, let's think about this differential. This is what? Let's not talk about the name here. So I know it's differential. It's called differential. So what does it mean? Anyone remember anything about the meaning of the differential? What? Remember anything? Yeah. Yeah, it wasn't you, but okay, you can talk.
If we think about it geometrically, if there's a function and we take a point and we take the slope.
Slope.
Yeah,
Yes.
and that's like.
Yes. So sometimes it's technically tangent slope.
Yeah.
So tangent slope automatically means that we are looking at geometric object, and what geometric object we're looking at is graph of the graph of what? Let me write it here. Of y equals to f of x at that point, right? So yeah, so I think that's the most common way to think about the meaning. Any other meaning can you think of? So I think this is the most big difference between Eastern and Western way of learning calculus. So when I taught calculus in America, the tangent slope was not the first way of talking, first meaning of these differentials. I think in the East, if they use the same traditional calculus book, I believe that tangent slope was not the first thing that appears in the definition or meaning of the differential. Have you heard about the rate of change? Yeah, but the rate of change is not a good subject to test you in the test exam, so it doesn't appear that much. But I think this one has to be appeared somewhere in your textbook whenever you find it. So when you think about this, the number here, it's not the average rate of change. It's an instantaneous rate of change, or rate of change at infinitesimal range of time. So instant rate of change. Of what? Change what? What do you change here? Value of what? Of a function. Yes, you're changing. You're looking at how fast the value of function is changing, because that's the rate means of the value of f of x. And where? Where do you look at those changes? Yes, you can see the change of the values by the graph, but you're talking about the instant rate of change. But whenever you want to see the rate of change, or even the change itself, you have to have certain point, right? You certain place where you see the rate of change or change. So you're doing it at x equals to c. So you see, I don't want to lose the information of this point and function at every meaning of this differential. And okay, so these two are very important meaning, but I want to emphasize one more thing, and the third one is the most important thing, because it is the meaning that connects to the meaning of the differential of the multivariable function later. But I'm not going to write it right now, but let me just give you an example to attack the tip over why this meaning is not sufficiently deliver the true meaning of this differentiability. So let's talk about the tangent slope. Let me give an example here. So my function f of x, let me write just f of x here, is given by x squared sine 1 over x and 0. So when x is not 0 and x is 0. So this is really weird function, because you have 1 over x. When x goes to 0, this goes really big. But sine function is periodic, so it cannot go out minus 1 to 1. So it's always bounded by x squared. So the amplitude is also decreasing. So you know that so we're not looking at far away from 0. We're only looking at around 0, because that's the point where I want to look at. So the question is f of x differentiable at x equals to 0? So can you think about the meaning and then answer this question? So think about the tangent slope. So we have to go through the graph of this function, and I hope I can draw it, but it doesn't really matter if I draw it by hand. So if you can use the Python right now, you can draw the graph of this function, something like this. So amplitude, the dotted line here, is going to decrease to 0. 0, actually 0, not this much. And it's going to oscillate infinitely many times as x goes to 0, right? Because 1 over x goes to infinity. There are infinitely many periods. So where is the tangent slope? Where is the tangent line at 0? So what do you mean by tangent line here? What do you mean by tangent line? So sometimes we take tangent line as something that is obvious, but obvious in the sense that the line has to barely touch the graph, right? And it cannot penetrate, it cannot intersect it transversely. It has to touch the graph at one point, right? At one point only, around that point, right? But can you draw any line that barely touches the graph at the 0? Imagine how it looked like. So amplitude is decreasing to 0, but it's oscillating infinitely many times, right? So how can you possibly give a line that is barely touches the graph at the origin itself and no other points? It can't, right? You're convinced that you can't draw any tangent line in that sense, right? So there is no tangent line here in our obvious sense. So either you change the definition of tangent line, or you have to drop the meaning of the tangent line as the meaning of the differential, right? So I'm not saying well, you have to choose one. I'm just saying that I just want to shake your idea of tangent line. Okay, that's all. All right, so tangent line is not enough to answer this question. I don't know I don't know about the differentiability by looking at the graph. So what do? I need to go to the definition, right? So let's think about the definition. How do we check? So definition is, well, that's always you have something that you have to consult whenever you are stuck at some concept, right? So mathematicians have devised this way. So I mean, this is the meaning of the word, meaning of the mathematical word, differentiability. So you always, like a dictionary, you always have to go to the definition whenever you are confused. So let's just think about the limit x minus 0, fx minus f0. So we want to find out the limit, right? So is x equals to 0 or not in the limit? I want to replace my f of x with the formula. So I need to choose between these two. Which formula should I use? Top or bottom? Top or bottom? Bottom for f of x? Top, yes, because x is not 0. X is close to 0, not 0. So that's something that you have lots of practice in your high school, because that's the place where most people make mistake. So I can replace x by x squared sine 1 over x. And what is f0? 0. Not because I plugged x equals to 0 here, but because I defined that way. Okay? You can't plug x equals to 0 because you have 1 over x. But by definition of x, I have 0. So x here. So you can ignore 0. So what is it? It's a limit. X goes to 0. X times sine 1 over x. What is the limit? 0. Why? Yeah, sine is always minus 1 to 1. And they have x multiplied. So no matter how much it oscillates, it's going to be 0. The size size of the value must goes to 0. So we know that it's 0. Okay, the limit exists. What does that mean? The function is differentiable. And what's differential? 0. This is the differential. This is the differential of this function. Okay? Okay, so by the same reason, can you find the instant rate of change of this function? What do you mean by instant rate of change? Well, it means that like you have a small interval and try to find the difference between the points at two ends of that interval and then find the rates. But since this function is oscillating, infinitely oscillating, whenever you try, I mean, it depends on which interval you're taking, which end of the interval you're taking, that might have a rate of change, positive or negative. It's like oscillating again. So it's hard to think about instant rate of change in that case too. But, so since we have the function which is already known to be differentiable, and we know that the differential is 0, we can now apply that fact to reinterpret the meaning of this differential, which is tangent slope and the graph. So let's think about this again. So it means that so f of x, f prime 0 equals to 0 of this function is 0. So it means that the tangent slope, so pretend that we have the meaning, correct meaning of differentiability here. And I think it's a good way of thinking about the meaning, but I'm not saying it's just completely wrong. It's just sometimes you can't just think naively of this meaning. But let's pretend that we want to put that fact, the differential, the value differential equals to 0 into plug into this meaning of differentiability. So it means that the tangent slope is 0 for this function. So tangent slope equals to 0. So slope is 0 means that it's horizontal line, right? And tangent means that it touches the point, right? So the point that it touches has to be the origin, and the slope of that line, whatever the tangent line is, has to be 0. That means it's just x-axis, right? So for this function, the tangent slope or tangent line is just x-axis, right? It's in this case. So let me write it this way. So this means the tangent line is x-axis. And what does it mean in instant rate of change? Instant rate of change is 0. What does it mean? What does it mean that you have instant rate of change equals to 0? Does it mean that it doesn't change? It's not that it doesn't change at all. Right? If it doesn't change, then it's just a constant function. Right? It's not that the change is 0, it's the rate of change which is 0. Right? So whenever you say a rate of change, you have to think about this meaning. So let me write it in an abstract sense. So what does that mean? It's the limit of the ratio, but if I drop the limit and if I take not infinitesimally small range, but just the small range, it means that my rate of change, instant rate of change, is almost equal to the average rate of change on the interval, let's say, c to x, assuming x is bigger than c. So you can also, I think you've probably seen this before in the high school or any other context. You can also write that the difference, the denominator is the difference in x-axis and numerator is difference in y-axis, and let's say denominator also is difference in x value from c, and the numerator is difference in f value at fc and from fc, right? So you can see that the instant rate of change is almost equal, approximately equal to the rate of these two numbers. So you can say from this approximation, in terms of this second meaning, as x changes by delta x, the value of function, let me write the value, let me erase this part, the value of f changes approximately by delta f. And what is delta f here? Since we have an equation, it's not exact equation, but approximate equation, delta f is given by f prime c times delta x. So This is the meaning of second meaning of instant rate of change, or differential. So it says as x changes by delta x, the value of f changes approximately by delta f, which is computed as approximately f prime c times delta x. So if you have instant rate of change, then you can estimate the change of your value of function according to the change of your x value. So here's an example. So, I mean, this is so obvious, but some people don't give a big meaning to keep, don't make a big emphasis on this. But let's think about the unit of velocity or speed. 10 kilometers per hour. What does that mean? What does that mean? It means that you go 10 kilometers for 1 hour. But is it really true? So if the velocity of a car is 10 kilometers per hour, does it mean that after 1 hour, does car actually go 10 kilometers exactly? It depends, right? It can change the speed, right? So it's wrong to say it goes 10 kilometers after 1 hour, right? So it says that so we can say in these two different ways. If the car maintains the same speed, then after 1 hour, it can go 10 kilometers. That's one way you can say it. Or another way of saying is, So after x hours, the car, whatever, moving thing, moves approximately by 10 delta, so 10x. Well, let's call it delta x, 10 times delta x. Okay? So if you plug in delta x by 1, then you're talking about very vaguely about the speed. But you can say, okay, 0.1 hour, 10 minutes, right? 6 minutes, right? Or you can say 1/60th, 1 minute. Or you can say 1 second, right? 1/3600. Then you can get a more accurate description of what 10 kilometers per hour is, right? That's the meaning of instant rate of change. So so the reason why I don't really care about the formula here, so I mean, I will explain more about the formula later, but right now you have to understand the meaning of the differential completely well in order to understand the rest of the parts. Any questions? Yes?
Yeah, how we can describe instant rate in one sentence, or we should like...
So this is the way of describing the meaning of instant rate of change. Yeah. Any other questions?
Did you use it's zero use because we know that t equals to 0, so multiply there?
Yes. So if you have f prime c equals to 0 as our example case, that means it's not always constant. It means that for small change, so I'll throw in small words here, small change of x from c, the value of f changes approximately. So you have to always put approximately words, approximately here, by 0. So because 0 is 0, which is f prime c times delta x. Okay. So now it makes sense. So what I mean when you see this. So if I change x by small amount from c, then this instant rate of change equals to 0 means that there's no change. There's no significant changes from the original value fc. Right? All right. So third meaning. This is the most important part. Third meaning. So look at our definition of the limit or differential. So we have f prime c, by definition, given as the limit of this ratio. And I'm going to rewrite this as follows. So put this number to the right-hand side and make it 0 on the left-hand side. and put this number inside the limit and also inside the denominator here, the numerator here. So if I take the same denominator, we have fx minus fc plus f prime c x minus c. Okay? So having the limit is equal to limit of this thing equals to 0. Okay? So I'm going to rewrite this part as Lx. Okay? Let me write it here. So definition, Lx is f of c plus f prime c x minus c is called the linear approximation of fx at c. So I think you guys knew this equation already. What about this? What does this formula represent? What is this formula about? Yeah, it's a tangent. The formula of a tangent line. Why do I call it linear approximation, not the tangent line? Because I said the tangent line sometimes means that it has a tangent to the graph, but in our differentiability, some function doesn't have a tangent line, even though it's differentiable. So we call it linear approximation. And also, I want to emphasize the meaning of the differential in terms of this linear approximation. So what does linear approximation means? Let me give a nice picture for now. So we have a graph, let's say, and we have a point C, and say this is our tangent surface, a tangent slope, and this is the y equals to Lx, and this is y equals to f of x. And why do we care about the tangent line? Because in a small view, in a small window around C, the graph of function is almost same as the graph of the tangent line. So you can approximate the value of actual value of function by the value of the approximation, right? Just a linear function. So when x is very close to C, f of x and L of x is very close to each other. I'm not saying they are the same, but they are close enough. Now, what does the differentiability says? This is the differentiability. Let me erase everything except for the last one. And let me just write it here again. So differentiability is exactly same as 0 equals to f of x minus this part, which is Lx divided by x minus c as x goes to c. That's the third meaning of the differentiability. What does that mean? It means that the difference between the function and the linear approximation goes way faster to 0 than the speed of x goes to c. So these are two differences. The first one is the difference between two functions, and this difference between the points, right? The real value. So if you want this to go to 0, the numerator must go faster to 0 than the denominator. So it means that the error of linear approximation decreases to 0 faster than x approaches to c. This is really important. I emphasize that the calculus, any calculus, whether it's a single variable or multivariable calculus, is about differentiability and integration. And I said that differentiability, a differential is all about linear approximation. So this is the meaning of the linear approximation in terms of differential. So when you have a differentiable function at a point, some point, then it means that you can take a linear approximation whose error the error that's estimating of real number, real value of function, is decreasing to 0 in a faster way than x goes to c, that point. So in other words, we call, as an abbreviation, the linear approximation is good approximation. So in other words, there is a good approximation. Okay, so what do you mean by good approximation? This is when we say it is a good approximation, when the error rate goes faster than the rate of x goes to c. So here, let me give an example. The obvious example that you guys all know, but had never thought about this in this way. So we have example of y equals to absolute value of x. So let's say f of x, sorry. So f of x. So this is not differentiable at x equals to 0, right? Why? You guys know this. The graph has a sharp corner. Sometimes you have a left slope, right slope. It doesn't change. They're not the same. Okay, so there are many ways to explain why, but let's thought about this case, this fact, in terms of the third interpretation of our differential. What does that mean? Since it's not differentiable, it means that there is no good approximation. There is no good linear approximation. So what does that mean? Whatever linear approximation, whatever linear function you take, it's not going to have an error rate decreasing fast enough to 0, right? The error rate, error will not decrease faster than x to c for any linear approximation. So here's the picture. So this is the graph of y equals to f of x, right? So I'm looking at this point, the origin. So let's pretend I'm going to give a linear approximation, which is the linear line, just the graph of a line. And I must pass through this point, otherwise it's not going to be anywhere close to approximation. So at least I need to know, I know that my line is passing through the origin. So I can draw many lines, like lines here, whatever the line, horizontal line. But it says none of this line will have an error which is decreasing to 0 fast enough, faster than x goes to, 0 here, right? Why? Okay, so let's say I pretend I have the horizontal line as my linear approximation. What's the speed of error going to 0, decreasing to 0? So this is the difference, right? This is how much the error of my linear approximation is decreasing. Of course it goes to 0. It's not about whether the error goes to 0. It's about the speed, how fast the error goes to 0. That's the important part. I'm not talking about whether error goes to 0. It has to go 0. I mean, if it's not going to 0, it's not even an approximation. It cannot be even called as an approximation. But I'm just saying that whether the approximation is good enough. So this is going to 0, but see, this is the 45-degree angle slope. So this length is exactly the same as this length, and this length is the error of two functions, and this is the difference between the x value and 0. So they are the same. They are linearly dependent, right? So even if I take any slope, well, maybe I can get, smaller and smaller errors. But if I make it smaller here, this side, then it's getting bigger this side, and it's also not as fast enough to make it to a good approximation. So this is very important, even more important than what you think, because if you don't remember this, you're gonna get lost completely when we talk about the differentiability of multivariable function. Okay. So any questions about this? All right, so I'm going to introduce some theorems. Maybe you don't, maybe you know or you don't, but this is important ones, so just mention this. So first theorem is mean value theorem. So I wish I can write a complete sentence, but pardon me because I don't have much time. So let's say f is continuous on the closed interval a to b and is differentiable on the open interval a to b, then there exists a point C inside this open interval such that this f prime C is equals to fb minus fa b minus a. So we can draw the graph of function, a nice graph